Good morning, everyone. I'd like to welcome you, sorry, Charles, to our last day of Fringe. And I'm very pleased to share this session with my collaborator, Takeo Tadono from JAXA. We are leading, and I'm Julia Kobanik from ESA. We are having a collaboration to further develop ROSE-L, but also LOS4 in the future. So JAXA is providing ESA with a lot of data sets to study synergies and complementarities of C and L band data. And some of the results of these collaborations will be presented in this session. So I'm pleased to introduce our first speaker, which is André Kalia from BGR in Germany, and he will speak about the characterizations of LNC band DINSA dataset in the Saar mining district in Germany.
Good morning, everyone. Thanks, Julia, for the introduction. Welcome to my presentation, Characteristics of LNC band Advanced DINSA datasets in the Saar mining district, Germany. The work was also contributed by my colleagues, Volker Spreckels from the mining company RAG and Thomas Lege from BGR. So one slide for the motivation and preparation of the Copernicus ROSE-L mission. We want to analyze the synergies of C and L band in a geohazard pilot site. Which one? The Saar mining district. And why did we choose this? Because it's an abandoned mining site in higher latitudes in the western part of Germany. You can see it with the right box on the right-hand side, the area of interest, and the area is characterized by urban subsidence and uplift. And there's also a cross-border phenomena of these deformations. The land cover is characterized by patches of forested areas, farmlands, pastures, and also, of course, urban areas. There are open cast mines, tailing piles, several subsiding and uplifting areas. I will come back in the next slide on that. There's extensive data of subsurface geology and mining activity from the mining company. And obviously we have the C-band PSI data from the ground motion services, whether it's from the German one or the European one. We have extensive terrestrial monitoring, including leveling networks, but also multi-sensor stations combining GNSS, time series, leveling, and corner reflectors, double corner reflectors for ascending and descending. A little bit of history in the Saar mining district. It has a long history of mining. So you can differentiate two areas. One is at the French-German border. And there was active mining until 2005, causing subsidence. And then after 2005, the mines were flooded and uplift happened. This is also the signal that you see in the European ground motion service and in the German one. And then a little bit north of it, there's active mining, coal mining until 2012, causing subsidence. And then two phases of flooding, causing first a small uplift or stable conditions after 2012. And then it's foreseen second phase of the flooding after 2025, and an uplift of about 20 centimeters is expected. To get you a little bit familiar with the study area, here's the Saarland border of the federal state of Saarland with this black line, and there are several mine water handling areas, and the boundary is shown with these blue lines, and the small blue dots are the plumb shafts where the water is pumped. And before 1969, the mining area was like this, quite big area in these gray colors. And then between 1969 to 2012, it has reduced because of the closure of the mines. And this green rectangles shows the location of these multi-sensor stations, MSSTs, with the corner reflectors GNSS, etc. And yeah, well, there are hundreds of shafts and openings, of course. To give you an impression about the corner reflectors and the multi-sensor stations, I have 3 pictures here where you can see them. So there's this double corner reflector with the co-located GNSS antenna. Yeah, and of course the electricity from solar panels. The location of the others multi-sensor stations are these red triangles, and the location of the 2 ALOS-2 footprints from descending and ascendings are also shown here with the green and the blue outlines. And to give you an impression about the GNSS time series, I plotted here the time series from July 2020 until September 2023. It's a daily mean measurements for 5 GNSS stations and respectively the east, north, and up components with the ±2 centimeter scale. And you can see several things, especially in the up component. You can see some seasonal variations, but also in the Anna Schacht, stronger subsidence. And the cause here is the very dry conditions in the summer, for example, in 2022. And you can also see on the right-hand side the top view where you can see the small horizontal component. And I will show you examples from these 2 areas in green and in blue with the solid outline in green and in blue. And I have to say that this is like a preliminary results because we just have 11 images for the ascending and 16 images for the for the descending data set. The observation time span is a little bit more than 2 years. It's a strip map observation mode with a high spatial resolution, 3 by 3 meters. And then for comparison, the Sentinel-1 dataset from the Ground Motion Service Germany, processed by GAV with the processor from German Aerospace Center, Mr. Eineder's group. And you can see we have a lot images, 325 in this case, and a long observation type span of more than 6 years. And obviously we are using IW observation mode from Sentinel-1 with 20 by 5 meter spatial resolution. And this is the area with the ongoing but declining uplift at the French-German border, so the southern part of the study area. And I plotted here the corner reflector from Loud and the corresponding PS in the time series. So the uplift is like 4.3 millimeters per year between 2015 and 2022. And comparing to the GNSS measurements on the bottom right, you can see that both time series show a long-term positive trend, but the Sentinel-1 time series has several outliers, especially between 2017 and 2019. Concerning the year 2021, you can see a GNSS, in the GNSS time series, a small negative value, also caused by the very dry summer. And you can also see a little bit of seasonal motion in the GNSS time series. And if you look at the long-term interferogram or the interferometric coherence of the ALOS data, covering a time span of a little bit more than 2 years, you can see that the corner reflector has a very high spatial coherence of 0.97. And regarding the PS density, I don't show the velocity map in this area because it is the very small stack with just 11 images from ALOS. But to give you an idea of the PS density, I plotted here the PSs as the black dots. So, and in the background is the Korean land cover classification. So you can see that compared to the Sentinel-1, we also get a lot more points also in the rural areas, the vegetated areas, the greenish from the Korean land cover, and obviously because of the higher spatial resolution in the cities and urban areas, also more than with Sentinel-1. So 200 PS per square kilometer from Sentinel-1 from the German-wide processing, and more than 2,000 person scatter per square kilometer from ALAS 2. And I also want to show you some velocity results from the other stack, the ALAS descending, where we have 16 images. The velocity scale in this visualization is plus minus 2 centimeters per year. And you can see in this location in Schneewiederhof, a landfill, that you can have a much higher PS density with ALOS compared to Sentinel-1 on the left-hand side. This is also the case in an active mining area for basalt mining. So the mining is in the southern part of this area, but in the mid and northern part, you can nicely see, this is a zoom in the mid part, that we can have more PSs in the partly vegetated areas with ALOS 2. This is what we want to see and what we want to use. This is the synergy from ALOS. So let me conclude. The multi-sensor station in Lauterbach is highly coherent in the 2 years ALOS 2 interferogram. The comparison with Sentinel-1 shows a similar long-term positive trend. And the observation with respect to the complementary characteristics from C and L band is, in this case, the higher spatial resolution, and then also the higher spatial PS density in the LS2 dataset. On the other hand, the higher temporal resolution of Sentinel-1 is also very, very important, especially for these nonlinear motions. And this work was the first test regarding the characteristics of L and C band in this area of interest. And we need obviously a dense and long L-band time series to perform the baseline monitoring of the small displacements until 2025, and then after 2025 to monitor the expected strong uplift. So to give you a temporal context, I just plotted the images that we already got with the filled blue dots from ALAS2 and what we would like to have with the non-filled points. And then, the start of NISA and the start of Rose L is also shown here to give you some context. That's all from my side. Thank you for your attention.
Thank you very much, Andre, for this nice overview of deformation in Germany from ALOS and Sentinel-1 data. Are there any questions?
Did you look at the effect of resolution on the L-band PS density? Degrade the resolution to see if you have fewer PS targets?
Yeah, obviously this is not a fair comparison because of the much higher spatial resolution directly causing a higher PS density in terms of numbers. So I've just looked visually, and of course in the cities there's a lot more PSs caused by the higher resolution, but because I see also much more PSs in the vegetated area or partly vegetated areas in ALOS, it makes me confident that also the longer wavelengths is contributing to a certain extent to this higher PS density. But yeah, as I said, it's still preliminary because I didn't expect too much. We have low deformation rates, relatively low deformation rates, and a small stack with a small time span. So if we get more images, what we want to do is to resample the data, the ALOS2 data to the Sentinel-1 resolution, and then make it a more fair comparison.
Thank you.
Any other questions for Andre?
Thank you. The velocities between C and X band seem to agree quite well. What did you do in L band for the referencing? How did you make sure you have the same reference? Did you do any special?
Mm-hmm. So the idea is to reference both data sets with respect to one of these multi-sensor stations. But now in this work, it's not like that. So the ground motion data from service from Sentinel-1 is referenced to other GNSS stations that the ones that I showed here from the company. Yeah. But the idea is to use one and the same GNSS stations for both data sets and then make it more.
Yes, of course. I know the EGMS data is referenced to the surrounding, but the L-band, you had to do a referencing.
Yeah, it's just the reference point coming from the PSI processing. It's just a stable, assumed stable PS.
Something in the vicinity.
Yeah. No calibration done.
Okay, Paul has another question.
Or I should say it's no datum connection, because the term calibration is also in discussion. Sorry.
This question is actually for Takeo. So for ALOS-4, it will show up on that map in 2023-24?
I will introduce later.
Yeah, okay. So, but the question relative to this is the plan for ALOS-4 to have ScanSAR mostly around the world, or will there be these high-resolution measurements at places like these mining sites? What's the plan for?
Well, yes, as Paul mentioned, ALOS-4 will be observed globally by the ScanSAR and strip map mode, probably 10 or 6 meters. So that much frequently L-band data will be available, combining with the NISA and ALOS-4 in the future.
Thank you.
Okay, thank you. I think it's time to move on to the next speaker.
All right, next speaker Francesco. The title is a soil moisture derived from ESA, experiment at the C-band and a contribution from L-band. Please.
Thank you. Let me see. Okay, so we are changing the topic a bit. This presentation is about getting to a product for soil moisture from INSAR. And I have some more experiments at C-band and just a few things about L-band. And of course, thinking of the deformation community, one day we have to also think back, how do we correct these effects in the phase coming from soil moisture? But this is not in this presentation, so. The physical principle is, I don't know how to explain it in a simpler way than this, is that when we have penetration in the soil, we have both penetration and so we have propagation. This means attenuation and amplitude changes and phase changes. And this happen at all depths. So the deeper you go, typically the more attenuated is the incoming wave field, and the more phase you accumulate. And this also depends on the soil moisture state, so these effects are larger if you have more water in the soil. And in theory, just in very broad terms, we are very sensitive to soil moisture with the INSA phase. When I think about, like, normally we say we can reach 1 millimeter at C-band with a bit of multi-looking normally. This means like a fraction of a millimeter of water, maybe 1/10 of a millimeter of water. And if we think that we see this, we sense this through a little volume of 1 centimeter, this is already 1% in volume soil moisture, which is a pretty good number. This is very theoretical, very unrealistic perhaps, but like we are very sensitive to water. So the method I use is based on closure phase. So you see that on the top, this is a closure phase from 3 images in January 2021 in Namibia. And this gravel plain. In the south, there are some sand dunes. And the idea is that from this closure phase, a bit of inversion, a complicated inversion, you can separate the contribution for the single dates. Like in this case, you see the 3 dates separated in this sort of moisture index that I have. And you see that the features, which are all superimposed and mixed up in the closure phase, they are like correctly unmixed and separated and dispatched to the 3 dates they belong to. And but of course, I'm not. This is a bit. This slide is a bit misleading in a sense that I'm not really taking one closure phase and I'm mixing a single closure phase. I'm not able to do that. But I'm taking many closure phases and jointly inverting them. I can then do this unmixing, let's say. So now I'm moving a bit more towards validation, like first validation experiments, and this is in Spain. It's 1 year of data with Sentinel-1, so 1A and 1B. Like you have most of the 6-day repeat. And then we have like 3 products. This is on a very large area, like the validation is in this case on the grid of the Copernicus climate change products, which is 1/4 of a degree. So it's a very large area, but I have like as a sort of truth or a reference, I take the ERA5 product, which is here in the solid line in the 3 graphs. It's always the same and it's correct. Like the first part of the time series is summer, so the soil moisture is low. And then you have the winter where you have the typical peaks and decays and all the stuff. And so you can see that the interferometry, let's say, so the INSA-based inversion, closure phase-based inversion follows pretty well the ERA5 product here. There are some peaks, some like sort of outliers, but I would say probably we have to check this, but I'm not so pessimistic about these things because of the time of the day and this kind of stuff. Radiometry is very reliable on the same similar resolution of the ERA5 product, so very low resolution. And then we have and perhaps here interesting is that the noisiness is a bit high, looks a bit higher, especially in the summer part, the first part of the time series. And then here the scatterometry is the interesting case, and maybe I have to spend a couple of words here. There are places where scatterometry doesn't work. In this case, it can be ASCAT, it can be Sentinel, but in this case, it doesn't work. Apparently, we have subsurface scattering. This is what they say. It might not be, but the thing is that you have like a very strange relationship between backscatter and moisture, like a U-shaped relationship. You can have very high backscatter in the summer when it's very dry. Then you have like a mid situation if it's a bit wet, and then you have again very high backscatter if it's very wet. So the inversion is a bit tricky in some places, and this is one of those places. And this doesn't happen everywhere, of course. These missions, they work generally, but there are places where this thing doesn't work, and this happens on different scales. Like this is a very low pass situation, but you can also have locally a lot of this strange situation. So in this first example, in this first study, the deviation I got from ERA5 and INSA was like less than 3% in moisture volume. Well, let's see. This is a more a larger scale. I don't know how to say. Another activity, another first very preliminary cross comparison of different products. This was done by CNR, the people in the hydrologists in Perugia. They have a lot of products from radiometers, CNX band, SMAP, radiometer also L-band here, and Gleam, some sort of model. Then they have this radiative transfer model of Vienna. And this is one case where the radiative transfer model doesn't work well. You see that even with some temporal and spatial filtering and trying to get the best the correlations with SMAP and Gleam, they stay in like 0.1, 0.2, so pretty low. And in this case, the INSAR is doing pretty well, as like the correlations are maybe 0.85. I guess could be better. They are not filtering as much as I think they should, because basically these models we are comparing with, Gleam or even SMAP, they have low resolution. So to compare, we should filter in the same spatial bandwidth, and I have a hard time to convince that, but somehow it's coming. So there will be some more widespread activity to test this on different sites. And then maybe here is this slide is about how do we see the interplay between what we can what we can do with backscatter and what we can do with phase. The figure on the left is from a paper by Wolfgang Wagner, and it's comparing ASCAT with ERA5 land. And where the correlation is high, the ASCAT product agrees with the ERA5, and when the correlation is low or even negative, which happens sometimes, the scatterometry has troubles. The model doesn't quite fit, and inversions are not so good. This happens typically in dry areas, like you see all a lot of northern Africa and Arabia, but also it happens also in the US and in Chile and in Namibia and in Central Asia, like all this Iran, Afghanistan, Kazakhstan, I don't know. And on the right, you have this map of C-band coherence, in this case, SAMA coherence, which is more or less where I would say that INSAR has a chance. And you see a lot of complementarity, I would say, like where INSAR works, more drier area in this case, because we have C-band, it's where scatterometry runs into trouble. So I would say the two can complement each other pretty well. And of course, maybe I will talk about this later again, but thinking of L-band, the coherence map will change, and we will have much more chances of doing high resolution soil moisture with INSAR. And we don't really know what will happen to backscatter, or I don't know. Here is another, it's a chart to show, to have an impression of what can happen with backscatter. Like sometimes where it doesn't work, because it works, of course, many times. But this is in Libya, and in this date, it's a change with respect to a date where everything is dry, so it should be a proxy for soil moisture change. And you see that the backscatter map doesn't have the same features as the INSAR-based inversion. You see sometimes the backscatter goes up when it rains. Sometimes even locally you can see all these white patches. It means the backscatter went down. And it's very hard to get the shape of the precipitation event, which is much more clear in the INSAR. And so this is one example. Because before you have seen like an example with time series, and this is maybe in space, you can see it a bit better. Okay, and then since we are talking about space, also the problem is the validation of these things. Nobody has moisture sensors in space with the density to validate these things, so it's very hard actually. But I've seen nice correlation with the land surface temperature, which seems interesting. Totally different band, totally different frequency, of course, and these products are derived from, the land surface temperature products are derived from thermal bands. So here you see the soil moisture from the INSAR, and you see I've circled here, highlighted some features, like some spatial features, which I think are very clear. And then this is the same from the land surface temperature from the MODIS sensor. And I don't know if I have to go back and forth, but the patterns are the same. And land surface temperature, of course, is not always available. Like you have clouds sometimes, and also the signals are very different in time. Like the land surface temperature signals, they decay and they disappear. Like after 24 hours, something like this in these desertic areas, they are just gone. But the signal from INSAR is much more long-lived, like even a couple of weeks, which makes me think, of course, that we are seeing something a bit deeper under the ground and which lives longer. It's the same spatial pattern, but temporal. It's not a story. Another example. This is Namibia. After a rain event, you see often that rain collects into channels. Some geologists call them paleochannels. In this case, I was able to, the coherence is very good, and even at C-band, and I was able to get to a product which posted at 60 meter, with 120 meter resolution in a Shannon sense, like that we have to sample twice, whatever. And then on the left, you're on a very similar, in the same place, of course, you see the backscatter change, very hard to recognize any feature. You can perhaps interpret a bit looking at the INSAR product. Like sometimes you see, okay, here it's a bit darker, but really the kind of sensitivity and spatial resolution that you can reach with INSAR in this case, not the same as what you can reach with backscatter. And just on the right, just one Sentinel-2 image, just to show that the features that I see in the INSAR are also present in the optical image, a bit enhanced here, just to get the features out. And but the difference is perhaps that the INSAR thing is we have a movie, and I'm going to show you a movie now. The Sentinel is like a static image. You get the same thing more or less, but INSAR is really changing and very sensitive to what's happening. And here's the movie. It's a little time series. Well, I think the dates are wrong there. It's from end of 2020 to March 2021. And so just a few months, every 12 days, because this is the coverage you have in this place. And you can see just a little zoom of the whole thing, what you can follow the time series, and you can see sometimes you have probably like a widespread precipitation event, so you see the features in these channels like here, and then sometimes you have more localized storms like this one. So you can see that the high resolution is really there. These things might be interesting also for weather forecast, because the initiation of convection is driven by the moisture condition on the soil. So like there are people doing very nice work predicting the convection based on the situation on the ground, and sometimes they have troubles, of course, if they're using the land surface temperature as a proxy for soil moisture, because it's not always available. But SAR, in theory, could see through clouds, so we can have this product more consistently if we just had enough temporal sampling. Okay, then I'm moving and closing with a couple of thoughts about L-band. Of course, I think L-band is very interesting for soil moisture, even though today we don't have so much data and time series and everything. This is a little experiment over Apulia in Italy with ELOS-2 data in the Roselle cooperation. The product here is sample at 200 meters, and the total time span is 3 years. I wanted to see this because I had done work in the past, but with a shorter time span. Well, the results are that over agricultural areas, it's difficult to have this coherence over the 3 years. So I have a lot of holes in the north, in this little peninsula. The coherence is is much better, so you can have, after 3 years, still good soil moisture difference. Of course, one could think here of processing like shorter time spans and then chaining them, and there are solutions. But yeah, so and the plot on the bottom is comparing the ERA5 and then the INSAR product and the SAR backscatter, and they all agree more or less, I would say, with a little bit of differences, but yeah. But of course, this is a very, very preliminary experiment, and especially over agriculture, we should see if we can shorten the time span and see if coherence can support a soil moisture product also there. In general, going from C-band to L-band, I'd expect more coherence and better coverage, of course, so that in general I can support longer time spans. And the sensitivity, I think, should be similar because, of course, we have less phase for the same amount of water because we have maybe less delay, but at the end we have more penetration, so more integrated water to go through. So in general, I think coherence will be better and we will be happy in general. Thinking in particular of Roselle, I think an interesting point is to look at which coherence we expect to get at L-band and which coverage then consequently we expect to have at L-band, and also which kind of complementarity we have at L-band with backscatter, because maybe so I don't know which this issues with subsurface scattering or whatever it is that's present already at C-band over arid or semi-arid areas might be worse or not, I don't know, at L-band. So, and of course, the ESA data are going to be very valuable to have like dense and continuous time series to be able to really to see these things through the seasons and all that. So I'm closing just with a little movie over northern Spain. This is this Ebro Basin. On the bottom you see my soil moisture product, and on the top you see the radar, weather radar of the hours, just the afternoon before the acquisition. The acquisition is on the evening, and then in the afternoon there was this storms. And this is another way of trying to validate these spatial patterns, which are otherwise very, so land surface temperature or weather radar. I don't know anything else how to show this on this scale. And then it's the end. So I have a couple of references, which are our old papers, where we had some first examples in L-band, and then you have just 3 examples just to see some nice pattern, precipitation patterns that sometimes you can capture with these acquisitions. So yeah, that's it. Thank you very much.
Thank you, President Kachari.
Just a quick question. Do you agree with the statement that at L-band, the radar backscatter would be more responsive to soil moisture than at C-band?
In the backscatter, I don't know. Of course, one hopes that we have less influence from vegetation so that we can pass through a bit better, right? I'm thinking for the phase, so probably it's similar for backscatter. But I don't know otherwise, yeah. It's very hard. But in really the backscatter, actually, people told me that they correlate with soil moisture, but it's really supported by the vegetation itself, so that somehow the water status seems to be like a good proxy for the soil situation, so that somehow, I don't know if we really want to get rid of vegetation, or it's very strange.
Okay, I just said that maybe the ground cover would be a significant factor in how you invert to get the soil moisture.
Yeah, I think so, yeah, for sure. Paul. least one.
It's kind of amazing talk. Thank you. Have you looked or thought of looking at the UAVSAR data sets? There's quite a few stacks of L-band data with both 12-day repeat and maybe even shorter repeat. That I know Jojo Gomba looked at it for a while back in 2018 and saw some very nice correlations with soil moisture. Maybe it would help densify your time series.
No, I haven't. Yeah, I haven't. But yeah, of course, this
It's
is
free and open. You can just download
yeah.
it.
They need, you know, they have to be co-registered or.
I think the interferometric stacks are co-registered automatically. Anyway, it's just a
Yeah,
thought.
thanks for reminding me, because there are so many data and sometimes one forgets.
Maybe to add on to this, from our campaign data sets, we have also like time series of ground-based L-band data, which could be analyzed for soil moisture.
Which campaigns? Sorry.
It's like, for instance, hydrosol, which was an
Hydrosol.
experiment in Barcelona. That's
Yeah.
C-band.
C-band, it's
But
I have seen that,
we are now at the moment acquiring data in Luxembourg with Marco Chini. And that's like WB-SCAT, so it has L-band and C-band data and soil moisture in situ measurements at the same
Yeah,
time.
we should not forget. Yeah.
Okay, thank you, Francesco. I think with this we move on to the next speaker, who is Takeo Tadono from JAXA, and he will report on the status of LS2 mission operation and CALVA plan for LS4.
Okay. Thank you, Julia, for introduction. So thanks to ESA to invite me here and take a good opportunity to collaboration between the C-band, L-band, or ESA and JAXA. So again, my name is Takeo Tadono from JAXA. Today I would like to briefly introduce status of the EROS operation as well as the development of the EROS-4. This is outline of my talk. And so I will start from the JAXA's Earth observation mission. This is briefly explain about the JAXA's Earth observation program. So that yeah, this line shows the current operated program. It consists of the 6 missions from the GOSAT to the GOSAT-2. And the right-hand side shows the future mission. It contains 3 missions, actually. So the EROS-2 is now operating very well, and it will be followed by the EROS-4 in the near future. And the GCON-W and the GOSAT-2 will be combining the GOSAT-GW as a future mission, which will be launched on next year. So, but today focus on the EROS series mission. So it was started from the EROS-1 satellite that was operated from the 2006 to 2011. And at that time, we have both optical mission and the SAR mission into the EROS-1 satellite, but that it divided to the EROS-2 and EROS-3. Maybe you know the optical mission of the EROS was followed by the EROS-3, but unfortunately it was launch failure on this March. Actually, it was very bad news in JAXA. But so as a result, the EROS launch target of the EROS-4 is now scheduled TBD. But as a good news, the successful H2A number 47 launched on the last week. It carried on the not Earth observation program, but also the deep space spectroscopy and the Moon Explorer. But this successfully will be pushed to the future Japanese program as well. Back to the SAR mission. Japanese L-band SAR mission was started from the JERAS-1 from the 1992 as a first generation L-band SAR missions. It was followed by the EROS-1 satellite with a pulsar instrument in 2006. And currently we have operated EROS-2 with a pulsar 2 It launched on the 2014 and still in orbit with good health condition. And in the near future, we have planned to be launched EROS-4. So that today many focus on the EROS-2 and EROS-4 mission. But actually, we are already starting the discussion, internal discussion for the future mission as a next generation radar instruments. Okay, this is overview of the EROS-2. Yeah, maybe you know about that, but it carried on the Pulsar-2 L-band sync aperture radar. And design mission lifetime is the 5 years and 7 years as target. So even in currently more than 9 years operation, yeah, it is under the good condition. Here, the summary of the orbit parameter here. It has some synchronous orbit with 12 local sun time and 24 LST. So okay. This is observation characteristics of the Pulsar-2. The satellite itself can be observed either right-looking or left-looking. And it has 3 major observing modes from the spotlight, strip map, and scanner. And this is a summary of the operation status 9 years. The upper left figure shows the amount of the remaining fuel, and left down is the power generation on board by the solar array paddles. And right upper figure shows the result of orbit control determination accuracy. So these onboard telemetry shown that it has still good condition. And right bottom shown the system evaluation, which is conducted every 3 months. But basically we can say that the EROS-2 and the Pulsar-2 has no anomaly now. So that we expect more longer mission life by the EROS-2. So the calibration result, this is summary of the calibration result of the Pulsar-2 in terms of geometry, radiometry, and polarimetry as well. So these are also still a good condition. And we are frequently calibrate activity using the ground reference data and the onboard calibration mode. So a little bit new information about the EROS-2 data distribution. Since 2022, we are starting to the all Pulsar and the Avenir-2 optical instrument of the EROS-1, as well as scanner data of the EROS-2, starting to the open free data releasing distribution, which is using the JAXA data distribution systems called G-Portal and the Google Earth Engine, as well as Amazon Web Services. For the EROS Pulsar-2 data, currently available only the scanner level 1.1 and the level 2.2, which is also rectified terrain collected data in a sales analysis data format. So that if you have interest in it, please access to them. So I move to the EROS-4. This is an overview of the EROS-4 characteristics. The orbit of the EROS-4 is same as the EROS-2, so that it can be done by the interferometry analysis using the Pulsar-2 and Pulsar-3 near future. There's a mission life is 7 years, and this is, well, yeah, okay. What is the improvement from the historical L-band SAR system to the Pulsar-3? This is summarized in the left figure. X-axis shown the observation source width, and y-axis shown the spatial resolution as just example here. So we are starting from the JERS-1, EROS, and EROS-2 now, and we expect much wider observation will be done by the Pulsar-3 near future. It means that the complete 40 days repeat observation could be done by the Pulsar-3 EROS-4 at least in a middle latitude area in globally. This slide summary of the prototype testing of the Pulsar 3 subsystems. Actually, it was already done, but during the development status phase, we are conducting several electrical unit tests as well as antenna tests. We are starting from the thermal vacuum test in the left-hand side, initial electrical and mechanical test, and antenna deployment test on the ground was conducted. After that, the Pulsar 3 subsystem hand over to the aerospace systems, PFT. After integration of the satellite itself to the Pulsar 3 subsystem, we are continuously PFT testing. Thermal vacuum test and vibration shock test and acoustic test, EMC, and finally we were done final electrical test. So as a conclusion of the PFT, aerospace, including the Pulsar 3 subsystems, had completed preparation for the launch. So that we are just waiting the H3 launch rocket now. This is characteristics of the observation specification of the Pulsar 3. Again, it has 3 major observing modes from the spotlight. If we compare with the Pulsar 2 one, it has a much wider surface with the dual polarization acquisition could be done in the spotlight of the Pulsar 3. Second mode is a strip map. Here we have also much wider observation as well as a quad polarization observation. Addition to that, we one observing mode called the ionosphere collection mode. It has the other split band bandwidth as a 10 megahertz, which will be used on the ionosphere collection in the atmosphere. Okay, in a scanner mode, it has about 700 kilometers wider surface with 28 megahertz bandwidth. And again, what is the capability of the insert processing between the Pulsar 2 and Pulsar 3? The summary is shown in the bottom table. Except for the scanner insert between the Pulsar 2 and Pulsar 3, we can done by the both Pulsar 2, Pulsar 3 interferometry processing. So that we are expect much longer time differences, subsidence estimations application. This is initial operation plan of the EROS 4. As a current plan, after launch the satellite, we have 3 months initial checkout, then 3 months for the initial caliber activities. During this initial caliber phase, we expensive calibration validation activities, collaboration with our PI science team, caliber science team. After that, we will start the regular observation with data distribution. Okay, and this is a little bit different topics, but the international cooperation is very important as well. So that this is a JAXA and ESA collaboration session, but not only with ESA, but also NASA, CSA, and AGI for the international collaboration. For the, especially for science and application field, we are together work for the ocean application and the land application as well. So that maybe we are looking for the much synergy collaboration by the multi-frequency analysis. So from here, I just briefly introduce some applications. This is our global mosaic and forest non-forest classification map using the historical L1 data. This is freely open to the public, available. The annual mosaic is available from the 1996 by the JS1, then 2007 to the 2010 by EROS 1, Pulsar 1. Then we are now producing the similar product by the Pulsar-2 L2 until the 2022. This is just an example using the global mosaics. This is a forest above ground mass biomass map derived by the ESA under the Climate Change Initiative project. Of course, combining and using the Sentinel-1 and the EROS-2 for the year 2020 of the biomass map, the ESA had a good job to create such global data set for the ground biomass, above ground biomass. Second example is the sea surface wind estimation. The Sentinel was already, and the Canadian CSA is already under the operation for the sea surface wind estimation. But we are also investigating to derive the similar product using the EROS-2 now, especially for under the cyclone typhoon activities. The third application is, of course, a disaster-related product. This is just an example of the estimation of flooding area using the time series Pulsar-2. But it also should be considered to combining a use of the other missions like Sentinel-1, NISA, ROSEL in the future. Okay, the summary, I briefly explain about the JAXA Earth Observation Program, and especially for LC's missions. As unfortunate news is the failure of the L3 with H3 launcher, which is a new Japanese rocket. This is terrible bad news in Japan. But as a good news, we successfully launched of the H2A number 14.7. It will be pushed to the move forward for the Japanese space activities, I hope. As the operation status of the EROS-2 and the development status of the EROS-4 are briefly explained. So actually EROS-4 is already ready to launch and just waiting the new launcher, H3, probably number 3 rocket. And the very important point is that collaboration with the international agency as well as the private sector will be much important in the near future to expanding the application field especially. Thank you very much for your attention.
Thank you, Takio, for this very nice overview. Are there any questions? Maybe Martin?
Takio, thank you very much for this presentation. Maybe you mentioned it, but on the operation plan, how many minutes per orbit can you operate ALOS 4? And do you also plan to operate it in a kind of mapping mode, similar to the Sentinels in Copernicus, or similar to NISA, so to be regular large areas? In which areas would these be?
Okay, thank you very much for your question. Probably the duty cycle of the EROS-4 will be the 50%, so the 50 minutes per orbit or something. And regarding the observation plan, we are also now developing the basic observation scenario for the global acquisition by the EROS-4. So it is now still under discussion with our users. But before launching the satellite, we will open to such information to the public. But basically, again, global observation will be done by the scanner and 10-meter or 6-meter strip map.
Okay, I think then Anna, please.
Thanks very much. It's great to have ALOS Pulsar acquiring brilliant data that we can use to enhance all of our science. I'm particularly pleased with the acquisitions that Alas Parsa has acquired over the polar regions, which is the area that I study. So I really want to support JAXA and the team to continue to acquire brilliant data over Antarctica and Greenland going forward. I think that there will be a really nice opportunity to do intercomparisons between the L-band data that you're already acquiring, comparing that with our products from C-band Sentinel-1 data, and also DLR TerreStar X-band data, and hopefully that will put us in an even stronger position to prepare for the ROSE-L mission launch by ESA in the future. Do you see any opportunities for collaboration on calibration validation campaigns in the polar regions using the L-band data that you collect?
Yeah, thank you very much. Yeah, I think so. Actually, we are continuously conducting the Earth observation research announcement. The another such EORA, we can have a good collaboration with every researchers, especially for some intensive observation for the research purposes. It's possible.
Okay, thank you. Is there another question? Okay, thank you, Takeo, again.
Okay, next presentation will be given by the Mr. Inabet, the case study of the EROS emergency disaster prevention for slope failure in the Sakai-mura. Yeah, something.
Okay.
Please.
Okay, so thank you for. I'm Ryosuke Inabe from Restec in Japanese company. I'm very happy to be here, and today I'd like to talk about how we use EROS-2 data for disaster mitigation and prevention, especially in landslide in our work. And furthermore, we would like to discussion to apply possibility of synergy of C-band and L-band SAR data. And this is my presentation contents. And first, in introduction, I will explain the occurrence of landslide in Japan. An overview of JAXA's EROS-2 emergency observation. In addition, explain the case study area in this research. And next, I will describe EROS-2 data and Sentinel-1 data in this study, and interferometry methods and using software. And then I will talk to results of the ESA analysis O2. First is in short term after slope failure, because detect presence or absence of deformation caused by slope failure. And before and after slope failure of 2020 to 2022, and after more SBAS analysis for long term, 10 years, using EROS-2 data. And so furthermore, discussion of applicability of Sentinel-1 data to complement EROS-2 SBAS results. And lastly, I will conclude my presentation. So this slide indicates an overview of the last landslide in Japan. According to the data released by MRIT, MRIT stands for Ministry of Land Infrastructure, Transport and Tourism. The number of landslides confirmed 795 cases in Japan last year. And besides graph indicate average number of landslides over the last 10 years, and has been about 1,450 cases. And so it's suggesting that a high number of disasters are occurring in every year in Japan. And today's presentation topics, slope failure had occurred in Nagano Prefecture, northern part of Nagano Prefecture. Okay, so JAXA conducting an emergency observation by EROS-2 when contacted by a ministry or a user to get informed to possibility of a disaster due to typhoon or landslide, earthquake, heavy rainfall, and so on. And so The results obtained from emergency observations reported to the ministry about 5 hours after the observation. And these emergency observations are conducted not only Japan, but also response to requests from foreign countries. And LESTEC supports emergency observation on domestic cases. And so this is an overview of today's topics landslide. And on May 9th, 2020, slope failure occurred along Nakatsugawa River in Sakaimura village in Nagano Prefecture. And these upper right images are captured by Sakaimura village survey. And this photo clearly shows the slope failure. And so Emily contacted JAXA to inform that the slope failure had occurred, and because Nakatsugawa River, so danger of a blockage river channel. So JAXA conducted a total of 4 emergency observations from 10 May 10th and June 1st by ALOS-2. And the lower image indicate the study area in this my presentation, and rectangle indicates area of interest. And north to south and west to east topographic profile is indicated right image, and you can see a relatively steep slope in east-west direction. Okay, so then we attempt to extract the disaster area by RGB color composite map taken by ALOS-2 observation, emergency observation, and previously observed image. And right image indicates ALOS-2 pulsar 2 RGB color composite, and red color indicates decreasing intensity. For example, changes from vegetation to bare soil. And cyan color indicates increased intensity, like residual deposits. And left and middle image observed by Sentinel-2 and true color image and before and after slope failure. And so as you can see, the clearly slope failure zone. And furthermore, in addition, this area is an abandoned vegetation area and still snow in early May. And so next, we applied to the ESA analysis to confirm whether the formation continued after the slope failure in this region. And next is satellite data, ALOS-2 and Sentinel-1A data. And first 2 scenes of ALOS-2 data is used for the ESA analysis because presence or absence for deformation to just after the slope failure, because yes, and 17 scenes data is used for S-bus analysis for long term, because deformation is long term or not. And Sentinel data is used for 28 scenes to verify if it could be applied to monitoring when ALOS was not observed during period. This study area is well known for its heavy snowfall, so we used only data in the non-snow season. And this slide is a method and using software. We use Gamma software for the inside and S-bus analysis, and threshold term and perpendicular baseline used for 730 days and 1,000 meters respectively in this research. And we will talk about the results of this research on the next page and beyond. This slide displays the results of the analysis from ALOS data and 14 days and just after slope failure. And right image is observed by Sentinel-2 optical image observed after slope failure. And this INSA results image color map shows displacement away from satellites in warm colors and towards satellites in cold colors. And According to this the INSA results, no signs of displacement around the failure zone, and so therefore it is considered landslide is not continuing after the failure. And this slide indicates a result of the INSA analysis about 2020 to 2022, 2020 to 2022, and now. Including this time of stroke failure and found subsidence or westward displacement upper part of the stroke failure. And right image, the landslide distribution map released by NID, and it's illustrating the past landslide area and overlaid on the left image. And so we believe that displacement is caused by landslide because detected area almost matches with past landslide and landslide areas. And furthermore, a detected displacement area is located upper part of the slope failure zone. And so we carried out the S-bus analysis next in order to survey the information for a longer period. This slide indicates results of S-bus analysis, cumulative displacement by S-bus analysis for LS2 data for each observation date, reference on October 2014. And it shows deformation from satellite in the upper part of the slope failure throughout the S-bus analysis period, and which increasing values closer to the failure zone. And this image, left image, indicates a cumulative displacement at 27 June in this year, which is the latest observation date. And the right graph indicates time series trend for each observation date at the number 1 to 4 point located in the left images. And so the formation away from satellite detecting the upper part of the slope failure in seen throughout analysis period, and the formation almost matches with past landslide areas. And so discussion of applicability of Sentinel-1A data to EROS S-bus results. And in this previous slide, we have identified trends in long-term landslide deformation in these study cases. However, more high-frequency monitoring is needed to find what factors causes landslide, such as this one. And so, in other words, this could allow for countermeasures to be taken if there is an inflection point of landslide velocity. Specifically, if it is necessary to keep observation for this purpose at least once every few months. And I think this task will be overcome when EROS-4 is launched in the future. Sentinel-1A was selected as the most appropriate data to overcome this task in current situation. So first, we conducted a DNSA of Sentinel-1A over about the same period of time in 2020 and 2021 and 2022 as the EROS-2 observation period to check its interferometric properties. And the results are shown on the next slide. And this slide is indicate the INSA results of EROS-2 and Sentinel-1A data respectively. The upper panel shows EROS-2 results, and the lower panel shows Sentinel-1A results. And it's about same time period respectively. And as you can see, EROS-2 keep coherence better than Sentinel-1A, and more it is possible to monitor to displacement. And for Sentinel-1A, because relatively short wavelengths and more than 1 year pair are greatly affected by vegetation, indicating that coherence are not maintained. So we perform the INSA in pairs per one return, so 12 days, and in the next slide shows the result of the 8 pairs for which coherence was retained. This slide results of Sentinel-1A DINSA results every 12 days about high coherence. And we applied Sentinel-1A data observed from the middle of May to October from 2020 and 2021 for DINSA analysis at 12 days interval. And 8 pairs with good coherence were acquired. And the image of each are shown on this slide. And next, we used these results to quickly check first whether they could be used to supplement the period when LS2 was not observed. So applying Sentinel data to LS2 sparse results, and we attempt to supplement 1 year from August to 2020. It is not observed LS2 data. So with 8 results of Sentinel-1A with an offset to the displacement for each observation determined from the displacement velocity for this period. And this value is not accurate complementary result because different incidence angle for 2 or 3 degrees of displacement, but to some extent it could be easily supplemented in this way. So furthermore, it can be considered that displacement may have occurred about the same rate during this period. So let me summarize my presentation. Short-term LS2 DINSA analysis for just after the slope failure because to detect presence or absence of deformation occurred by slope failure. As a result, no trend of displacement was observed after the slope failure. And a long-term S-bus analysis by LS2 data showed displacement around the disaster area throughout the analysis period. And in addition, these results were making for disaster warning by local government. Yes, in order to detect displacement with high temporal resolution for landslides that occurred in this study area, so we examined the possibility of applying Sentinel data to cover a period of time when LS2 did not observe. As a result, we found that interferometric coherence was kept in part of the pair for one observation cycle, and it was possible to use for this task, but it was not sufficient, so we plan to continue this study. And lastly, we look forward to the upcoming launches of Sentinel-1CD and LS4 for expecting the synergy of C-band and L-band data. And we like to thank Ministry of Lands, Infrastructure, Transport, Tourism for supporting our work. Thank you for your attention.
Thank you very much presentation. Are there any question, comment on that? Yes, please.
So I understand you were using the ALOS-2 strip map mode. Did you also look at the ScanSAR to get the more frequent observations?
We use strip map mode because LS2 emergency observation is observed by strip map mode usually.
Any questions, comment for him? Okay. Okay. Thank you very much for your presentation.
Okay. So with this, we continue with the last speaker of the session, who is Claudio De Luca from Area CNR, and he will speak about the on the PES bus processing chain new developments for the generation of SOCOM-1 advanced DINSA products.
Thank you, Julia. Hello, everyone. Let's start with motivation of this research activity. essentially everybody knows the great impact that the DINSAR technology and consequently the satellite SAR system have for the emergency scenarios and also for civil protection purposes. This fact is pushing the space agencies to invest in new satellite SAR mission, and in particular in the last years big investment have been done for L-band satellite constellation. I'm talking about forthcoming mission like Roselle, NISAR, Pulsar 3, and also about the radio operative constellation like Falcon 1 and Pulsar 2. In my presentation, I show you some Falcon 1 constellation, some characteristics of this constellation, the development of procedure for the large-scale monitoring analysis with Falcon 1, Peace bus results, that is the processing chain that we use, implemented for Falcon 1 data, and I will conclude my presentation with some open issues and some advices also about this constellation. Anyway, lastly, I want to thank also the Italian Space Agency because this activity is in the framework of the DINSAR FRINGE project funded by Italian Space Agency. So let's move to the SAOCOM constellation that is composed of two twin sensors, SAOCOM 1A and SAOCOM 1B, that for DINSAR application works in strip map acquisition mode. So we are talking about more or less 50 kilometers square of the footprint. Here on the right, we have just a comparison over Napoli Bay Area of the footprint of SAOCOM 1 compared with Sentinel-1, 215 kilometers more or less. Okay, it works. This constellation has a resolution of 545 meters for single and dual polarization. Obviously, L-band, we are talking about 23.5 centimeter, and with a revisit time of potentially 8 days, because there are two sensors, but acquiring in a strip map mode, if you want to guarantee a global coverage, this revisit time grow up to more or less 1 month. And this system, combined with the Cosmos SkyMed, generates the system CSG system, where the satellite flies on the same orbit, so can be also used for specific application together. So let's move to this slide. Essentially, when we start working with Falcon 1 data, we don't want just to generate DINSAR results, but we want to implement a large-scale monitoring service with Falcon 1. To do this, it is very important and fundamental to implement some procedure to merge, let me say, the adjacent slices, okay? Because to guarantee that the user area of interest is fully covered by your data. This is just an example over Napoli Bay Area. On the left, we have the yellow square, that is our area of interest, that is not fully covered by the Falcon 1, by just one slice of Falcon 1. So you need to just merging these two slices, and then you have just one SLC, and you can also just cut over the user, the area of interest to improve the performances and to reduce the processing time of your processing chain. And to do this, that is essentially quite straightforward for Sentinel-1 and also for Cosmos SkyMed, is not for Falcon 1. Indeed, you need to implement some procedure more to make this merging procedure possible, okay? First, you need to make a slice resampling on a common temporal grid, and you need also to make a phase shift estimation and compensation. The first procedure, why you need to make a resampling on the same temporal grid. Essentially, if we consider two adjacent slices that in this slide are reported in red and blue one, okay, these adjacent slices have fortunately the same PRF. Good, but you have a sort of temporal shift between these two slices that can, and this shift can reduce, let me say, the quality of your differential interferogram. So you need just to resample the adjacent slices with respect, in our case, we use the first slice, but you can use any slice you prefer. But this procedure is not enough to guarantee an high quality of your differential interferogram. Indeed, if you try to perform an interferogram by merging 2 slices for the master acquisition and 2 slices for the secondary acquisition, as you can see in this slide, and in particular in the zoom here, there is some phase inconsistencies in the overlap area between the adjacent slices, a sort of phase jump. And why you have this problem? Because the adjacent Saucon 1 slices have not only different temporal reference, but have also a different phase reference. Indeed, if you, in a very easy way, estimate the phase difference in the overlap area for the master acquisitions and for the secondary acquisitions that are reported in this histogram here on the E and F histogram, you can see this phase difference in the overlap area is different from 0, and it should be 0. So you just need to estimate this phase difference, to compensate this phase difference, and to improve the quality of your differential interferogram. Another experiment that we perform with this data, a 300 kilometers long interferograms over the Italian Alps, retrieved by merging 4 slices for the master acquisition and 4 slices for the secondary acquisition, before and after applying the phase shift estimation and compensation. On the top you have the result before the implemented procedure. As you can see in the zoom, there are the phase inconsistencies that are gone when you apply the implemented algorithm. The results is very impressive. I would like just to spend a few words about the great coherence that you can retrieve with the L band over the Italian Alps. This interferogram is incredible, let me say. Okay, let's move to another problem. That is not a problem of the sense of the constellation, but actually maybe it's a problem of the ground segment that release several kind of orbit. I mean, in some case, we have a big problem with a low accuracy of this state vector. The CONAI releases the online very fast orbit that are generated and calculated with GPS on board of the satellite. So believe me, the results are very bad. As you can see here in the first and in the third interferogram, you have this big phase ramp over your interferogram. Then after 2 days after the acquisition, you have the online fast orbits that are high quality orbit for sure, but the more accurate orbit are released 18 days after the acquisition. So if you need to work with, for example, I don't know, a post-seismic acquisition, so you need to go an interferogram as soon as possible, and you can not wait 80 days. So you need to implement something to reduce the impact of this, let me say, phase ramp. This is just a block diagram of a piece bus strip map processing chain implemented, and starting from the SLC acquisition up to time series generation. When you arrive, let me say, to differential interferogram, you need to implement a step more, let me say, that is the estimation of this phase ramp, and you can apply different method to do this. If it depends by the accuracy that you want on your differential interferogram. A very easier way is to estimate a correction, the first order correction, just in the hypothesis of your phase ramp is a plane of phase, so you can apply a 2D Fourier transform, very, very easy. Or for example, our implementation, as you can see in this, is well described in this paper here, where you try to correct the baseline, in other words, to correct the state vector on the SAR acquisition. So in this way, you have a second order correction that can improve the quality, for sure, of your differential interferograms. Then, when you work with the band, yes, you have to spend time to implement, we think, new idea, new algorithm, new approaches, let me say, for the phase unwrapping procedure. Because you can benefit from the high coherence of your interferograms with that band. You can benefit so of your small baseline in interferogram. As you probably know, our approach for piece bus process in our processing chain for the phase unwrapping procedure is the well-known extended minimum cost flow that is essentially a 2D plus 2D phase unwrapping. You have a temporal phase unwrapping and then a spatial phase unwrapping. Essentially, it works in this way. You have a data set. This is a Saucon 1 data set over Napoli Bay Area. Okay, you connect the acquisition. You connect, yeah, yes, okay. You connect the acquisition with the Edeloni triangulation, where essentially your the arcs are your interferogram. Then you apply the small baseline constraint, so you remove some arcs and you move from a Delaunay triangulation to a so-called reduced Delaunay triangulation, and in some cases you need also to reject some acquisitions that are totally far from the average orbital tube. And yes, usually we work with this kind of network, but with L-band, you can benefit of a lot of small baseline interferogram and coherent interferogram. So our advice is to implement different approaches to benefit of this redundant interferogram network that you can generate with L-band system. And this is very useful not only for the estimation of the deformation, but also to make your inversion phase moving from the interferogram to the acquisition more robust also with respect to the phase unwrapping error too. Okay, let's move to some results. This is the piece bus processing analysis with the Saucon 1 over Napoli Bay Area. This is the mean deformation velocity map, and we have just some plots of a pixel located in major deforming area. For example, on the left we have a huge damp affected by a continuous subsidence just far from the Campi Flegrei. Then we have a pixel in the middle, here located in the Pozzuoli hamlet, so affected by the uplift, affecting, yes, the Campi Flegrei since a lot of years. And then we report a profile of the Campi Flegrei, of the mean deformation along the Campi Flegrei, that clearly showed the well-known radial geometry of deformation pattern field affecting this area, that are in good agreement with the analysis that we do with also other sensors, other bands, and other constellations. So let's move to another example, actually to another hazard, natural hazard, that is actually the first hazard in Italy that are landslide. This is Tuscany region, and here we report some example of landslide affecting this area, also in urbanized area, so very dangerous. And here we have a pixel on the left, in Zeri region, and on the right in the Fontana Fredda hamlet, okay? But you have a lot of phenomena actually just in this area. I would like to spend just a few words more about the great impact in terms of final measurements point that you can retrieve with the L-band analysis. This is the Sentinel-1 analysis that we provide each 6 months for the Italian ground motion service for the Italian ministry. Okay, we want just to compare the coverage with the L-band analysis. This is a zoom. The impact in terms of final measurements point in this rural area is very impressive. And if you zoom in some specific cases of landslide, in particular, on the left here we have the analysis with the Sentinel-1, where you are able to detect, yes, the impact of this landslide, but on the right you have the L-band analysis, and you are able to fully reconstruct the body of your landslide. In terms of deformation rate, yes, in the common pixel we can see that are in good agreement with also Sentinel-1 analysis. So I don't need to convince you about the improvement of the coverage with L-band in rural area, but actually we have an improvement for the distributed scatterers. But you can also improve the final measurement point also for persistent scatterers. This is just an example in Rome. Here, this is the Bridge of Music. That is a metallic infrastructure, okay? On the left, we have the Cosmos Skymed piece bus high resolution analysis, where you can see we have no pixel on the bridge. It's a very strange thing. On the right, we have the L-band analysis, and we suppose, where we have a lot of pixel on the bridge, okay, and we suppose that actually the problem of the loss of coherence in the X-band is due to the strong vibration of this pixel impacting the X-band like a noise. Okay, while the L band is more robust to this kind of effect, generating, yes, the time series that is this is a pixel on the bridge, where is clearly evident also the seasonal behavior of the thermal dilatation of the metallic infrastructure. Another application, okay, this is a tragic event, this is the area affecting the tragic event of Turkey in 2023, earthquakes. Okay, this is just actually a small piece of the full analysis that we performed that has been presented by my colleague Pasquale Striano, where we reconstruct the full body of the deformation with the SAOCOM 1 data. Okay, even if we are working with L band, 23 centimeter of wavelength, it's not enough to guarantee the, yes, it's more robust to face ambiguity for sure, but it's not enough to estimate the meters of deformation affecting this area. So the pixel offset is a perfect application for this kind of situation, okay? And so we have also a strip map acquisition mode with a pixel spacing of more or less 4 meters, so a good pixel spacing, a good spacing. Okay, so we estimate also the azimuth pixel offset, and for sure for ascending and descending, you have also the slant range pixel offset that clearly show the differential movements along the faults affecting these and locating in this area, and by benefit also of 2 equations for each track, because you have an azimuth solution and also slant range solution. You can combine all this information with this approach, for example, but also other approach to reconstruct the 3D field, deformation field. You have here on the left the vertical component, in the middle the east-west component, and the north-south component on the right. Okay, let's move to the last 2 slides, Julia, I promise, okay. An advice, okay, a recommendation for the user of SAOCOM 1 data to do not use the data processed before the 5th July 2021, because there is a problem in the processor, probably due to, we have no access to the data, so probably due to the use of online very fast orbit in the processor that can generate this kind of very bad results in the same slice. Okay, you have these phase inconsistencies, strange behavior and loss of coherence that are, if you asking to Konai to reprocess this data, the results indeed with a newer version of the processor are absolutely good and perfect. Okay, last slide. Just few days ago, we were working on Litli Rutur, sorry for my bad pronunciation, the eruption in Iceland, the eruption of the volcano in Iceland. Yes, we generated the SAOCOM 1 interferogram that seems to be very, very good, coherent. Yes, you are able to see the pattern of deformation, maybe also some big fringe due to the ionospheric effect on the area. But the very strange thing is this one, when we try to apply the pixel offset technique, that where the result are absolutely unreasonable, in particular in azimuth, where you have this deforming strip affecting the image. But if you pay attention to the coherence, interferometric coherence, this is the same coherence, just differently saturated to emphasize this effect. This effect is clearly evident also in the coherence. So there is something, probably ionospheric effect, impacting the electromagnetic properties, impacting the amplitude of the signals. This is the reason you can see this also in the interferometric coherence. So we are working on that. It's very nice stuff trying to filter out this kind of effect. So that's all. This is the first time that we work with a huge stack of L-band image. So we are doing a lot of experience waiting for the future mission like NICER and Roselle. So thank you, everyone. That's all. Thank you.
Thank you. Thank you very much, Luca, for this very interesting insight into SAOCOM time series and very different applications. I think we can learn a lot from this. Are there any questions for Luca? There's one up there.
Since you're processing this area with multiple sensors, do you have any comments on
Can
the
you
noise?
please? Yes. Okay.
Since you're processing the same area with multiple sensors, do you have any comments or observations about the noise levels in X-band, C-band, and L-band?
You just compare the results with the C-band and L-band at the moment, and with the CX band for Cosmos Comet for high resolution application. Do you want to know something about
the noise properties or the uncertainties?
Yes, we are working on that actually, Piyush. Okay. I can give you a specific value about this. Okay, but as I show you for the high resolution application, yes, there is something impacting more the X band and less the L band, but we are working on that.
Okay, there's another question up there from Eric first.
Did you look at the range spectrum for the ionosphere?
Yeah, for the last slide, yes, we applied the split spectrum, yes, but it's not enough to, when you apply the pixel offset, you have the processing on the amplitude, okay? So yes, actually, to be honest, but we worked just a few days ago on this. This is the last slide for this reason, okay? But also applying the standard pixel, standard split spectrum, it seems that there is no a big impact of ionosphere, to be honest. Seems that I don't know if ionosphere, solar storm, or something like that, seems to impact more the amplitude than the phase of the image. But yes, we try to see the impact of ionosphere with the standard split spectrum technique, but it seems not impacting enough.
All right, thank you very much. Very interesting presentation.
Thank you,
the question I have is, I've seen a few presentations, and yours is one of them, where you compare L and C band time series, and you say they agree, more or less. There was a nice example there of the slope of the displacement being the same. Have you any thoughts at this point in time? If we look ahead, we see that there are several L-band SAR missions coming with fairly regular acquisition patterns. We also have Sentinel-1 first generation and Sentinel-1 next generation, where as a user you know exactly what you get in terms of time series. And have you any thoughts as to how to combine them? Just, you know, there has to be, you can treat them separately, which is what's being done, but
yes.
My guess is that there are ways of combining the information that go beyond simply treating them as separate time series.
Yes, actually, also within the project that I just mentioned in the first slide, okay, the InfraFrame project that we, thanks to this problem, we had access to this data actually, okay. Yes, in this project we also implement some procedure too, because it was a multi-bandwidth and also multi-platform project, okay, where we try to do this, to combine all these information that are coming with L-band, NICE, Roselle, okay, we have Cosmos second generation, we have Sentinel-1, yes, so we are trying to do this to benefit of all peculiarities of all bandwidth, okay, because I think that this is the future, this is the aim, to exploit all this information and try take benefit of all these sensors and all this constellation. The L-band, for sure, you have a big coverage everywhere, okay, yes, but with X-band, C-band, maybe you have a more accuracy in estimation in the urbanized area, so you have to implement some weighted technique that, yes, weight the results of CX band in a properly way, let me say. But absolutely, yes, we have to work in this way. This is the aim. Otherwise, why you have all this constellation? We try to put together in the same thing. Okay.
Are there any other questions? If that's not the case, I'd like to thank first Luca again for his presentation. And then we have the roundtable discussion now and the questions, but I think Marcus wants to announce.
I have a short announcement. So I see several chairpersons in this room, and my colleagues told me that an hour ago we are still missing many of the summary slides for the summary session that starts in, well, within half an hour, 11:30. So please send in the summaries and get ready to present. Thank you.
Thank you. So we thought to use the time here, since we have a JAXA representative, and we just renewed this collaboration for L-band data acquisitions with JAXA, to hear from you what the community would like to have. So with this collaboration, just to repeat, we are focusing on developing ROSE-L and also to support the development of LOS4. So any application you could think of that might be helpful, we could try to arrange data acquisitions or archive data, but it always has to serve the need of supporting our mission development. So are there any comments from you or what would be required? Yeah, there's one comment up there.
Yeah, thanks very much. I think that it would be great to have more acquisitions over the ice sheets, so Antarctica and Greenland, but very specifically, it would be good to have them over a range of different snow and ice types. So, for example, we might see different performance on wet snow in comparison to very dry snow environments, and similarly, steep topographic terrain, like mountainous regions of the Antarctic Peninsula, might have different performance levels than, say, the flatter parts of the ice sheet in the interior. Equally, one of the benefits, one of the things that's been a complete game changer over the last sort of 8 years has been the very dense temporal sampling that we've had from Sentinel-1. It's been fantastic to have 6-day repeat acquisitions. We're looking forward to them coming back as soon as 1C launches. But again, it would be great with the ALOS data to have a similarly dense time series in some of these regions, so that we can see how the noise varies, over time in a consistent location rather than only having snapshots. So I'll put that out there as a starting point. Data sets with interferometric capability as well, of course, in addition to the amplitude information that we use for our products.
Okay, thank you for this feedback. We will bring it into discussion. Any other points? Okay, there's one comment down here. The lower one, and then we go up. Yeah, didn't see you first.
I just said I will second that. That means I agree with that recommendation, and I would encourage that. Thank you.
Thank you.
So maybe one comment on, let's say, a more direct connection or joint processing of different bands there. I mean, we are still maybe a little bit discussing whether we should stack up Sentinel first generation, ROSE-L, really close to each other, mimicking same acquisitions within minutes or so. So I was wondering if such a situation could be recreated, for instance, with ALOS Pulsar and Sentinel first generation, because I'm thinking now, I mean, people are showing this problems with the atmosphere, or especially now with the ionosphere. And I think this is really a strong point of having the same acquisition geometry, same time, that you really can assume to have to observe the same atmospheric state. So if you now do data-driven methods, if you do inversion of atmospheric phase screens from PSI stacks, you can literally assume the same tropospheric state in the L band and in the C band. You have a scaling knowledge how you can scale a ionosphere from C band to L band. So these kind of approaches, I think this would really help them to get a better feeling of this. And I mean, I guess, if you consult the solar cycle, right? I mean, we had the last maximum in 2012, 2014, which was not impacting these constellations and things we're seeing now at all. So the past years, it was smooth sailing, so to say, from the ionosphere, but this will now really catch up. And the next 4 or 5 years, we will get really more struggling with this kind of things. So getting more in feedback or experience with these type of things, I guess this would be useful.
Okay, well, thank you, because that's something we haven't looked too much into yet. There are a few data sets available, particularly over CIs, where we have tasked ALOS data to be like almost at the same time as C-band data. And if you are interested, we can have a look in the data, and you are happy to check what is there and to suggest what we could acquire in the future. Maybe also to advertise here from ESA side, because you mentioned ionosphere, we will issue an ITT for an ionospheric study, hopefully by the end of the year, where we will aim to study the effects in L-band data. Are there more comments or questions? Okay, Malcolm, please.
I'm not sure I'm allowed to make recommendations to my own agency, but just to come to one or 2 points. One was a very good one I just mentioned right now, which is and it illustrates nicely the point I was trying to make about the combined use of L-band and C-band for time series and for not just treating them separately, but using, for instance, results from C-band perhaps to address things such as ionospheric correction. So I would encourage the community to think further in terms of how to combine C and L-band in a sort of optimized way. The other observation I made, so I'm just building on what was presented and not inventing anything new, just to be very, very direct. There was some nice examples of new applications, for instance, using the phase for soil moisture, where, as far as I understand, you get a sort of average soil moisture over the interval of the actual interferogram that you're using to generate the phase, but which lacks a lot of validation at this point in time. And the point of validation of some of these new products is one that was made, and I was just wondering if in addition to sort of campaigns and these types of things to address it, where I think agencies can also work together quite well and put together funding. I was also wondering, in addition, some of these phenomena can be studied at high resolution with the support of, for instance, ground scatterometers. There's a sort of renaissance, at least in Europe, of a number of ground scatterometers that allow you to study in great detail what is happening at a small scale, of course, at the field scale, but they could be used to address perhaps the potential of these new products in trying to decouple, for instance, intensity versus phase signals and what they mean.
And maybe to add on, the campaign data from ESA's campaigns are all freely available on our website.
Yeah, just to add to that, we had discussions in several sessions about how it's actually the phase closure that shows a strong correlation with the soil moisture. So that's something that probably ESA could support more studies on.
Maybe I can also quickly respond to this. So for the development of ROSE-L, we designed a science plan, and we have several studies defined that will be kicked off in the next years, focusing on questions like soil moisture, land, ocean modes. Okay, there's another comment?
I'm making my usual comment. In general, for this studies, what I think we need is regular and long time series. So this is what, maybe we have some ESA, we have some SAOCOM now as things are popping up, but this is what's really, it's, when you're trying to develop something, it's not having a global coverage, which is important, but having a consistent time series somewhere, maybe over different line types, of course. So if ALOS-4 can help with this, of course, welcome. If NISR is coming, super happy, so anything.
Yes, we are trying to started building up time series, but the orbit time of ALOS-2 is not that long anymore. So, for instance, Andre for the surface deformation had to wait quite some time until he could even start the analysis to have sufficient data sets available. We are very much aware of this, and we are trying our best to address this and to generate some time series. Any other comment, question? if that's not the case, I would like to close the session and thank all the speakers for very useful and good presentations, and also for JAXA and another colleague from Japan traveling here just for joining this session. And I think we can really take this into the future collaboration. Thank you.